everybody, welcome to part 2. So in this first video, we're going to talk about interference in general. But let me back up and first talk about part 2 deals with phenomena, optical phenomena, where we use what we call the physical optics model. So if you recall in part 1, we had the idea of the electromagnetic wave, but we used a simplified ray model or geometric optics model, because we were primarily interested in just the direction that the light was traveling. So we were able to do things like describe reflection, refraction, image formation, and then even dispersion if we did remember that there's a frequency and wavelength associated with the wave. But some phenomena, for instance interference phenomena, the geometric optics model is too simplified. So you have to consider what I call the full-blown wave nature of the electromagnetic radiation. And again, that's sometimes called physical optics. Now we're going to look at just a few examples of interference. There are lots of different types of interference that can occur with light. In fact, interference is a phenomenon common to all types of waves. So water waves, sound waves can interfere. Waves on a string can interfere, but we're going to look at light waves. So we're only going to look at a couple examples, but what I want to do first in this video is just describe general interference. Now we are going to make some assumptions here, which will be fine. We're going to look at two-wave interference, so we'll just consider two waves interfering. And you can have more than two waves, but two waves will be enough for us. We also are going to consider that the two waves have the same frequency. And that may seem restrictive, but it really isn't. And you'll see in the examples we look at, that's a fine assumption. And there are a lot of phenomena, interference phenomena, where you can make that assumption. The other thing we're going to assume is that the two waves, the electromagnetic waves, they have the same oscillation axis for the fields. We're going to focus on the electric fields. So what we're going to assume is that the two electric fields, as they're oscillating, the axes are parallel. So for instance, they're both oscillating along a y-axis. The reason that is important, you'll see, because in general, if I have some point in space, let me just label that point P, okay? And let's say I have two sources of light, source 1 and source 2. And both of these happen to send an electromagnetic wave to point P, and they overlap, right? So there you go. There's one wave traveling along that ray and another wave traveling along that direction. So I can still use rays sometimes in the physical optics model to show direction. And that's supposed to be straight, not wiggly, but please forgive my stylus drawing. Okay, now, again, I'm assuming that these two waves have the same frequency. Okay, now, there's something in physics, we love to give fancy names sometimes to things. It's known as the principle of superposition. And what that says is, if you have two waves arriving and overlapping at some point P, if you want to get the net wave, you just add the two individual waves. Okay, so what that would look like is, if we're looking at the electric field waves, we would say the net field as a vector is the first electric field value at that point P plus the second value at point P at a particular time. But the fields are vectors, right? So this should be a vector sum. But by assuming that we have the same oscillation axis, that means we're either adding the two values of E if they point in the same direction, or we're subtracting the values if they point in opposite directions. So what I'll be able to do is just add up their values, E1 plus E2, if I allow them to be positive or negative. So that's how we'll keep track of the direction, just plus or minus. Okay, now, if you recall, the actual harmonic waveform, these are the summary notes from part 1, the harmonic waveform for our electric field is going to look like that, right? We can either use a cosine or a sine. So these harmonic functions are set up already to give me either plus or minus values. So that's really convenient. So really what I'm going to be doing, according to the principle of superposition, is just adding up these harmonic functions, okay? And I'll get the net field. And then the intensity of the light is going to be proportional to the net field amplitude squared. Okay, so I'm interested in what is the amplitude. When I do this sum, I'm interested in the amplitude of E net, because you may recall from part 1, the intensity is proportional to the amplitude squared. Oops. I'll just write it like that. Okay, so we're interested in the amplitude of E net. Okay, now, to help us visualize this, and we'll come back to this notebook here and talk about path difference and wavelength. But what I want to do is I'm going to go to Desmos, which you guys may be familiar with Desmos. It's a really nice graphing calculator, and you can make all sorts of plots, and it's free. Desmos.com if you want to play around. So what I've done here, and you can see over here in this panel, I've created two waves. I call them Y1 and Y2. And Y1 has an amplitude of A1, and then it has a frequency of F1, right? So if you notice, I'm using the cosine function. Now I am taking, if we go back here, I am taking my x to be 0, okay, just for convenience, because I want to look at what's happening in time. So we could consider x to be 0 and still see what's happening at this point in time. So I've written it as cosine of 2 pi f1t. 2 pi f is omega, okay? Plus, I'm allowing a phase angle. You see right here, and this will be convenient. So I can have a phase angle if I want, right, to shift my harmonic wave. And I want that capability. So what I've done is I've written the phase angle as q times pi over 180, right? Because I need radians in my argument. So q is down here. I can change q. So for instance, right now I have q equals 0. So this phase angle phi, q pi over 180 degrees, that phi is 0 right now. Okay? Now, if you notice, I've written, and here's a plot of y1. And I've set f1, as you can see right here, to 50. Okay? And again, that value really doesn't matter. It's just the way I did this mathematically, 50 gives me that wave. Now again, look, this is y on the vertical and t. I don't know if you can see the t, but there's a t over here. So this is what the wave is doing at a particular point as a function of time. Okay, so you see that harmonic oscillation in time. Now, y2, I'm going to write as a2, its own amplitude, times the cosine of 2 pi f2, that's omega 2 times t. Right, and I haven't written a phase angle there. So I can make these two waves in phase or out of phase by whatever angle I want by manipulating q. Okay, now I am going to choose f2. You can see right here, I'm going to make f2 equal to f1 because that's the case I want to look at. And for right now, I'm going to make the two amplitudes equal. You can see A1 is 1, A2 is 1. Okay, so they're equal. All right, so where is wave 2? Well, let me click on wave 2. And you may have noticed that this thing is turned green. Wave 2 is green. Wave 1 is blue. Well, right now, I have them completely in phase. So they're right on top of one another. So these waves are completely in phase. The phase angle difference between them is 0, right? This phi is 0 right here. So they're completely in phase. Okay. Now, I can make them go out of phase by varying the q. In fact, let me just increase the q, and you can see now how the two waves are are out of phase. Now, completely out of phase would be when q hits 180, because up here now, I would have 180 times pi over 180. I'm adding an angle of pi. So my phi becomes pi. And you recall from trig, right? If I shift harmonic function by pi, then it basically inverts the wave. Okay, and you can see now that the green wave and the blue wave with equal amplitudes are completely out of phase, right? When the blue wave is hitting a value of 1, full amplitude in the plus direction, the green wave is hitting a value of -1, okay? So now the question comes up, what is the superposition of those two waves? Well, I just add up the values. So let me go back to 0. So this is where there would be no phase difference between the two waves. And now I'm going to add them. So you can see right here, big Y is just Y1 plus Y2. So I'm going to go ahead and add these waves. And what am I going to get? Oh, I get that red, right? That red wave. Oh, I actually get a really big amplitude. Yeah, that makes sense. In fact, I get twice the amplitude of one of the individual waves, right, when I add them up, because they are fully in phase. So if these were two light waves arriving at point P and they were completely in phase, there's no phase angle difference between them, you're going to get a really big amplitude to the net electric field wave. You're going to get a really big intensity at that point, right? This is called, in fact, we would call this perfect constructive interference. The interference, right, is really just the superposition of the two waves, right? So when the waves interfere, they're superposing. So this would be perfect constructive interference. Now, what happens if I have a phase difference of pi between these two waves of equal amplitude? Can you picture what's going to happen to the superposition, to the big Y, the red wave? Let me go ahead and do that. Oh, there it is right there. Q equals 180, so this angle right here now, this extra angle is pi. The waves are completely out of phase, and when I add them up, I get exactly 0. This would be called perfect destructive interference. So if the two light waves arrive at point P and they're completely out of phase, meaning a phase difference of pi, or 180 degrees, you're going to get 0 intensity right there. Okay, that's pretty cool. Now, what if at point P the two waves arrive and they're not perfectly in phase, and they're completely in phase, and they're not pi out of phase? So let me just vary Q. Maybe it's something like that. Well, when you add them up, you're going to get something, an amplitude that's something between 0 and the maximum amplitude, right, which is double the amplitude of the individual wave. So you'll get something in between. So if the two light waves arrive at point P and they're not completely in phase and not completely out of phase by an angle of pi, radians, then you'll get an intensity that's somewhere in between 0 and that maximum intensity. Okay, so everybody see that visually what's happening? Okay, so let's go back to the notebook then. So this was one point P, right? But these waves are going to overlap at more than one point. So there might be another point right here where if you look at the two waves that are arriving from the two sources there, because of the difference in path that they have to travel, they may be completely out of phase. So maybe at the original point P they were completely in phase, and now at this point P they're completely out of phase. So when you look at this, you'll see a really big intensity or bright point at the original point P, and you'll see no light at this point P. And then there might be another point here where when the two waves arrive, they're somewhere in between those two extreme intensities. So when you look at this area of overlap, you will see what we call an interference pattern. You'll see some points that are really bright, some points that are completely dark, and then some points in between. Now, before we get to and focus more on the path difference, let me just go back to the Desmos plot. We've been assuming that the amplitudes are equal. And if that's the case for the two light waves, then you will get no light when you have a pi phase difference between the two waves, right? If the amplitudes are not equal, let me change the amplitude to wave 2, so that it's smaller than that of wave 1. Let me click off the superposed wave. So let's suppose that wave 1 again is the blue wave and wave 2 is the green wave. Let me put them back in phase. So I'll set 2 to 0. Well, when I add these up, I'm still going to get something big, but it's not going to be as big as it was if the green amplitude was the same size as the blue amplitude originally, right? But this will still be the brightest point when the waves are in phase. Similarly, if I make them completely out of phase by pi, right, I don't get 0 if the amplitudes aren't equal. Okay, oops, and I don't know why. What happened to my wave 1? That's interesting. Oh, I'm sorry. I was looking at the superposed wave. Yeah, you can see the red wave, right? So the blue wave is wave 1, the green wave is wave 2. They're completely out of phase by pi. So I don't get 0, right? But the red wave, the superposed wave, does have the smallest amplitude possible. As I vary this phase angle, the amplitude will get bigger. So I'm going from pi back to 0. You can see the amplitude get bigger, 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 bigger. And when I hit 0, that'll be the biggest it ever gets. Okay? So if the waves don't have the same amplitude, you still have the brightest point when the waves are completely in phase, and the darkest point, or I should say the dimmest point, when they're completely out of phase by pi, but that's not going to be 0 intensity. Okay, now let me get back to the notebook, because what I want to focus on is path difference, because that's how we're going to get this phase difference. So I'm going to write, let's write the E1, right? And I'll just call the spatial axis x, the distance, the path that the light is traveling. I'll call that axis x, like I did in the summary notes. So this is going to have some amplitude, right, E sub m1, and I'll choose a cosine, and then we have kx. Doesn't matter if I choose a plus or minus. Let's just say I take an omega, okay? All right, and I'm going to write it like that. And let's suppose that wave 2, right, I can write like this. Now, on purpose, I didn't choose a phi for wave 1, and you'll see why. Okay, so let's suppose I have two waves that look like that, mathematically. Well, right now, those two waves are completely in phase. They're going to be peaking at the exact same time, right? And they're going to be hitting 0 at the exact same time if the x value is the same, right? So, for instance, if x equals 0, then these guys are going to be completely in phase. But let's suppose that to get to a point P, and I'll draw another picture here because that one over there is getting cluttered. Suppose that wave 1 travels to get to point P right here. It travels some, let's say, x1, right, to get there. And let's suppose that wave 2 has to travel an extra distance. So maybe it has to travel x1 plus, let's call this delta x, okay, to get to point P. So what's going to happen when they get to point P? Now, I'm going to assume that x equals 0 is right here, okay, for both of these guys. So they're going to leave in phase. All right, well, mathematically, watch what happens. I'm going to write, when we get to point P, let me scroll down so I have some more room. When I get to point P, I'll write that. So at point P, E1, after traveling that distance of x1, right, it's going to be E sub m1 times the cosine of kx1 plus omega t. And then wave 2, when it travels that distance of x1 plus delta x, right, that's going to be equal to em2 cosine. And I'm going to distribute the k, so I'm going to get kx plus k delta x plus omega t, right? Okay, now look at those two arguments of the cosine. Notice the two cosine functions are out of phase by this k delta x. You can think of this now as some phi that I've added to E2. So the question comes up, right? What are the possibilities when I do the superposition? Well, look, if this phi equals 0, right, then they're going to be in phase. Well, how can that be? Well, that could be if k delta x equals 0. But physically, that doesn't make sense because then delta x would have to be 0. But we're assuming that these two waves, right, have traveled a different distance. Although I do note, though, if they traveled the exact same distance, these guys would still be in phase. That makes sense because they started in phase. If they travel the same distance, they'll still be in phase. So 0 is nice, but that doesn't really help me, right? Well, I guess it helps me in telling me that if they travel the same distance, they'd still be in phase. So what's another possibility, though? Well, when will cosine hit the exact same value if I add an angle to the argument? Well, to me, right, it seems like that would be 2 pi. That would, again, make them in phase, right? So if that extra phi was 2 pi, these two cosine values would be the same. Well, what about if they were 4 pi? Yep, they'd still be in phase, 6 pi. Okay, so let's focus on the 2 pi first. So what that means is if I remember that 2 pi over lambda is the angular wave number, look at this. I can put this delta x in terms of the wavelength. In fact, the delta x is going to be 1 wavelength. So if wave 2 travels 1 extra wavelength, if these guys started out in phase, they're still going to be in phase, and that is going to be a bright point at point P, a maximum intensity. Interesting. That does make sense, though, because look, let me go back to the Desmos plot. If you look at one of these waves, let's look at wave 2. See, 1 extra wavelength, that's just a time of 1 period, right? So in 1 period, if the wave, let's say, started at an amplitude, a positive amplitude value, 1 wavelength later, right, 1 period later, I should say, because this is a time axis, it's going to be at that amplitude, that full amplitude again. Or if it started out at some other value, it doesn't really matter what value, 1 period later, it's going to have that same value. So these two waves are still going to be in phase. But I said that 4 pi would also work, right? Because if I have 4 pi added to a cosine argument, I'm still going to get the same value. So 4 pi, 2 pi over lambda delta x, that leads to delta x is 2 wavelengths. Yeah, that makes sense, because if the extra path is 2 wavelengths, that's 2 periods in time. I'm going to have the exact same value. So in fact, if delta x is equal to an integer times the wavelength, this is going to be an intensity maximum. If these waves left in phase, this is going to be an intensity maximum. Now, what about an intensity minimum, right? What's the condition there? Well, for that condition, we need this angle phi to be, what, pi over 2? That would work. If I add, I'm sorry, not pi over 2, pi. I need phi to be pi. Because if phi is pi, right, I'm shifting the cosine by pi radians, that's going to flip it, just like we saw in the Desmos plot. So if phi equals pi, then this is equal to k delta x. These guys are going to be completely out of phase. And I should put completely. In phase means, yeah, they're right on top of one another. Out of phase generally means they're not right on top of one another. So completely out of phase, that means you've got pi phase angle difference between them. Okay, so if that's the case, and I remember that k is 2 pi over lambda, then I find out that delta x is equal to, what? Half of a wavelength, right? Yep, it's lambda over 2 if I solve for delta x. Again, that makes sense if you look at a cosine or sine function right? So look at that green wave, right? Right now, again, let's assume at x equals 0, it's at its amplitude, its full amplitude value. Half a wavelength, that's half of an oscillation. So that's half of a period. Half a period later, oops, it's going to be at its most negative value. All right, that makes sense. So, but pi is not the only possibility, right? I could have 3 pi. That should give me completely out of phase. If I add 3 pi to a cosine, right, I'm going to turn it into a sine. Okay, so that's going to give me delta x is equal to 1.5 wavelengths, or 3/2 of a wavelength. That makes sense too. Okay, so what we find out is if delta x, and you can write this a couple different ways. I'm going to write it as integer plus 1/2 wavelength. Then this is going to be an intensity minimum. And if the amplitudes are equal, remember this minimum would be 0, and this maximum would be 4 times the intensity of one of the light waves, because you're getting double the amplitude, and the intensity is proportional to the square of the amplitude. But you'll see this again when we talk about specific types of interference with the double slit and the grating. I'll be hearkening back to these conditions. Okay? All right, I've spoken long enough. If you have questions about this, just let me know. But in the next video where we do the double slit, we'll get much more specific. Okay, bye-bye.